I'll speak about my work, and it was joined with Maxim Babenko and Tomasz Kuczymiak and Paweł Gawryczowski. Actually, we study a very simple problem. So we have a string of length n, and we want to build a data structure which will answer two types of queries. The first query is maximal suffix query. We give you a substring of t, and we want you to find the lexicographically maximal suffix of this substring. And the second type of queries is the minimal suffix queries. So given a substring, we want you to find the lexicographically minimal suffix of the substring. So for example, if t is this string, AB, ABC, and we are given its substring BAB, then its maximal suffix is BAB, and its minimal suffix is AB. So my interest to the problem, yesterday we discussed that everybody lies about their motivation. So this was my motivation. My interest to the problem was born when I saw this picture on Twitter. So we are in Russia, and I can show it to you. Here it says suffix array, a suffix array in Russian. And this is a classroom at Moscow State University. And I know for sure that nobody except for Maxim Babenko, me, and Roman Kolpakov doesn't do stringology at Moscow State. So I started asking around, and it turned out that the picture was taken at ICM International Collegiate Programming Contest, whatever. And this is a solution to the duck-win-duck problem introduced by my high school friend, Vasily Astahov. So the problem was like there was a Disney character, Duck-win-Duck, and he was to protect New York City from some enemies. And the problem can easily be reduced to the maximal suffix problem. And they claim that they have a solution with n log n plus q time, an offline solution for the maximal suffix problem, and n plus q space. I've never been able to make them to write the solution down. So there is like this short draft of the solution. So I'm not really sure it exists, but this is what they claim. But we know that stringologists can do like a lot of substring queries, much more elaborate substring queries. For example, we know that the minimal and the maximal suffix problem for all prefixes of a string can be solved in linear time. This is a famous result by Duval. And it will be important for us, so please remember it. Then there are periodicity queries, like you can find the shortest period of a string, all periods of a substring. You can find all occurrences of a substring in another substring. This is a beautiful paper by Tomasz and the Polish group. I think it's on archive only, it's not published yet. Then cyclic covariance queries for substring, compressibility of substring. And maybe I forgot to mention something, and please forgive me for this if I forgot. So my question was, we know how to solve for these really difficult substring queries fast. And can we do something better than was proposed for the very simple queries, maximal suffix queries? And of course, when you ask about the maximal suffixes, it's very natural to ask about minimal suffixes. So we started our work last year, and this was the paper by Maxim Babenko, Ignat Kolesnichenko, and me. We presented a solution with linear space for the minimal suffix problem and for the maximal suffix problem. For the minimal suffix problem, the time was a little bit ugly. It was log to the 1 plus epsilon n time. And for the maximal suffix problem, the query time was logarithmic. So let me just 2 slides to explain what were the main ideas of our solution, because we reuse some of these ideas in this year's work. So for the minimal suffix problem, it's just one lemma, actually nothing. So I think that the first thing which pops up in your head when you ask about the minimal suffix problem is to start with the minimal suffix of the whole string, starting inside this substring. So if tm is the minimal suffix starting inside the range, then you might think that tmj, this suffix trimmed at the last position of your substring, is the answer. Well, unfortunately, it is not. So here is an example for you. If we take again the string BABC and its substring ABA, then the minimal suffix starting inside ABA is ABAC, and we trim it, and we obtain ABA. Well, it's not the minimal suffix of ABA. The minimal suffix is A. But we can say that the minimum of TMJ, and its shortest border, well, it's not necessarily exists, but if it exists, we take it, is the answer, so like this. Okay, here's TMJ, we take its border, and the minimum of these two is the answer. So how can we find M? We can find M very easily. We just need suffix arrays and range minimum queries on the LCP table for it in constant time. And for the shortest border, actually, we can use the result by the Polish group. Like the shortest border of any substring can be found in log to the 1 plus epsilon n time. So that's it. That was our solution to the minimal suffix problem. For the maximal suffix problem, actually I like it a little bit more than our solution to the minimal suffix problem, because it doesn't use any black boxes, only combinatorics on word. So again, we start with the maximal suffix, this time with the maximal suffix starting inside our substring. And we can prove that TMJ is a prefix of our answer. Well, we have a prefix, but now to reach the answer, how can we do this? We can take just another step. Now we can take the maximal suffix starting inside the range IM-1. And we showed that if TM1J starts with TMJ, then it's another prefix of our answer. It's a longer prefix of our answer. And if it doesn't, then TMJ is the answer. We can return it. So now we have an algorithm. We take M, then we take the next prefix, and so on. The problem is that there can be too many iterations of these next prefix iterations. For example, if a string consists of all letters A, then the next prefix will be, each time it will be just one letter longer than the previous one. But this can be easily overcome. We can do this. We can notice that if we have starting positions that are located closely, to each other, then they form rounds, and we can skip these rounds in constant time. This is not very simple. We have to use like longest common prefix tables and range minimum queries again, but this can be done. And each time now, after each step, we will have a prefix that is at least twice longer than the previous one. And so we have logarithmic time. So what we did this year, how we got to this year's CPM. Again, we have linear space solutions for both problems. And for the minimal suffix problem, we presented a series of solutions, a trade-off. We have tau query time and n log n over tau construction time. For the maximal suffix problem, we have optimal query time, constant query time, and linear construction time. But I think it's much better than the solution of the previous year. And I forgot to mention that the team is a little bit different, but it is. So how we obtain this? Let me start with the minimal suffix problem. The main idea is to use canonical substrings. What is this? So we define a logarithmic number of canonical substrings for each position j. This canonical substring, they end at this position, j, here. We require the first substring to be a substring consisting of one letter, tj, and the last substring to be the whole range, t1j. And this canonical substring, they must cover the interval 1j regularly. What does it mean regularly? It means that the length of two consecutive substrings, they differ by a factor at most 2. So what do we need them for? So the main property of these canonical substrings is here. If we know that the minimal suffix of the canonical substring SL is longer than the previous canonical substring, SL minus 1, then we can compute it in constant time. I will not explain how to do this, but I will explain how we use it. Okay? So remember, we had this lemma. So if we take the minimal suffix starting inside our substring, trim it, and then the answer is either TMJ, the trim suffix, or the shortest border of the trim suffix. So the border, it cannot be too long. It cannot be longer than TMJ, than the half of TMJ. And the longest canonical substring, because we have this regularity, it cannot be too short. It cannot be shorter than the half of Tij, so not shorter than the half of TMJ. So okay, we know that TMJ can be computed in constant time. The problem is beta, the shortest border. So let's assume for now that beta is the answer, that it is the minimal suffix. How we can compute it then? So let's take, oh, I forgot to mention, but if we have this longest canonical substring in Tij, and beta is short, then we have that the longest canonical substring, it actually contains the border, it contains beta. And now we can take not the longest canonical substring containing beta, but the shortest canonical substring containing beta, okay? So let the shortest canonical substring containing beta be Sk. So beta is the answer. It's the minimal suffix. It's smaller than all suffixes of Sk. So it must be the minimal suffix of Sk as well. And what do you know? We know that it is longer than the previous canonical substring. It's longer than Sk minus 1. So we can compute it in constant time. But there is one problem left. We do not know how to compute K, right? So how can we compute it? We use bit vectors for this. The bit vectors are defined as follows, very simple. The bit L is set if the minimal suffix of SL is longer than the previous canonical substring. So Sk is simply the highest set bit in the interval ij. And of course, we can compute it in constant time using standard bit vector operations. So this way, we can obtain constant query time. I will explain you how to obtain tau query time a little bit later, okay? So now we have constant query time, but we want to get this n log n construction time. To get the n log n construction time, I haven't mentioned like any particular choice of canonical substring, and actually this constant query time, it works for any choice of canonical substring. But to get nice construction time, you need a particular choice of canonical substrings. And here we get this ugly formula. But actually, it's very simple if you understand where it comes from. So take a look at the second term. We need it so that all canonical substrings for a fixed m will start at multiples of 2 to the m. So many canonical substrings will start at the same position. They will be prefixes of each other. And to compute the bit vectors, of course, you only need to compute the minimal suffixes of all canonical substrings. Yes? Then you will be able to compare their lengths and lengths of the previous canonical substrings, and you will get the bit vectors. So our task is to compute minimal suffixes of canonical substrings, and many of them are prefixes of each other. They start at multiples of 2 to the m. Also, they cannot be too long. See here, it's not longer than 2 to the m plus 2. So they all are prefixes of blocks starting at multiples of 2 to the m, and short blocks. So what can we do? Remember, I said you to remember the algorithm by Duval. And now we can use it to compute minimal suffixes of all these canonical substrings. So for each fixed m, we need linear time to compute minimal suffixes of all canonical substrings starting at multiples of 2 to the m. And we have log n rounds of Duval's algorithm. So in total, it's n log n time. And now I will explain you. So we have now constant query time and n log n construction time. And I will explain briefly how to obtain tau query time and n log n over tau construction time. So we used bit vectors, right? And in bit vectors, we indicated which canonical substring is interesting to us. And now we will indicate if a group of tau consecutive substrings is interesting to us. So if it is interesting, if the answer is in this group, we set a bit. Otherwise, it's 0. So now we have for a query, we apply the lemma I mentioned before to a group of tau consecutive canonical substrings. And it takes tau time to consider each of these substrings and to compute the minimal suffix for it. And then we take the minimum of them, and this is the answer, tau query time. And for the construction time, actually, there will be log n over tau rounds of Duval's algorithm. And n multiplied by log n over tau, we get n log n over tau at the time. So here is a nice application of our result. We can compute Linden decomposition, the Linden decomposition of a substring quickly. You have already heard of Linden decomposition, so I don't have to explain how useful it is. I will quickly remind the definitions. So Linden string. I know it's usually a Linden word, but I use string, so it will be a Linden string. So a string is a Linden string if it's strictly smaller than any of its rotations. For example, ABC is a Linden string. It's smaller than ABCA, BCAA, and CABB. And the Linden decomposition of a string is a factorization of the string into factors S1, S2, Sk, where S1, S2, Sk are Linden strings. It is possible to show, this is a theorem by Chen, Linden, and Fox, that there exists a unique decomposition, Linden decomposition of a string. And we also know that the last factor must be the minimal suffix of a string. So now we have a corollary from our result for the minimal suffix problem. We can take a substring, we can compute its minimal suffix, and it will be the last factor of the Linden decomposition of our substring. For this, we need tau time, right? And now we need to compute this power. And it actually can be done in constant time, using just suffix arrays, longest common prefixes, and range minimum queries. It's a little bit technical, so it's not here, but it's in the paper. But overall, we get tau k time for computing the Linden decomposition of a substring, where k is the size of the decomposition. So now let me briefly explain the main idea to the maximal suffix problem. So again, we combine canonical substrings, the same canonical substrings, and ideas from the previous year. So we take the longest canonical substring of our substring ij, the query substring, and we have two different situations. The maximal suffix can be either shorter than this longest canonical substring or longer. If it's shorter, so we have here the maximal suffix. It must be bigger than all suffixes of Tij. So it's bigger than all suffixes of the longest canonical substring, S. So it is the maximal suffix of the longest canonical substring. And the maximal suffix of canonical substring can be found in constant time. It's similar to the minimal suffix problem. So the question is, what if the maximal suffix is longer than the canonical substring. We showed that then we can compute its starting position, p, in constant time. And the idea is actually very simple. It's just the idea from the previous year. We start from the maximal suffix, starting in this remaining substring. So we trim it, it's long enough, it's longer than the half of our substring. And then we start our next prefix iterations and run skips. You remember that each time after applying either the next prefix iteration or a run skip, our suffix length, our prefix length increases quite a lot. And so we'll need just constant time to reach this p. This is the idea. And the details are in the paper. So here is a brief summary of our result. For the minimal suffix, tau query time and log n over tau construction time. For the Linden decomposition, tau multiplied by size time, query time and log n over tau construction time. And for the maximal suffix, constant query time optimal and construction time optimal. So yeah, I have like a list of open problems for you. It's like very annoying that for the minimal suffix problem, we cannot get an optimal solution. So probably it's because the minimal suffix problem is not symmetrical to the maximal suffix problem, because the minimal suffix is actually an empty suffix, right? And we have this restriction. We ask it not to be empty. Is it because of this or not? We do not know. So the second question is related to the first question. It would be interesting to understand what makes, if it is harder, what makes it harder. And I think I should also give at least a partial answer to the question we got last year. So if we have the minimal suffix problem and we have an answer for it, if we have the maximal suffix problem and we have an answer for it, what about all suffixes that are in the middle? So if we are given a substring and we ask to find the lexicographically case smallest suffix of a substring, how much time do we need? So in our paper on archive, we give a solution. It's a very short solution, actually, with a log to the 2 plus epsilon n query time and linear space. And we actually can give a better answer, but it's not written down yet. So thank you.
Okay, thanks, Tanya. Any questions for the speaker? Maxime first.
So do you know the complexity of the problem in the comparison model?
No.
Short answer. Moshi? Yeah.
So what is the better time for number 3?
The better time, logarithmic.
Oh.
Okay, so you know how to answer it in O of n space in order of logarithmic time.
Any further questions for Tanya?
Then coffee break.
Yeah. So let's thank her again.